Good afternoon. Let me first recapitulate what we had done in the last class. In the last class, we started by discussing the distance ladder, the cosmic distance ladder, and I told you that the only direct method of determining distances outside our solar system is through parallaxes, and parallax is essentially the change in the angle at which a particular star appears as the earth moves around the sun, and from this we can determine the distance to stars up to a few kiloparsecs, not beyond. Now, beyond that, I also told you that there were indirect methods based on certain physics. So, the first method was fitting to a main sequence. So, this was the main sequence and you have to fit open cluster to the main sequence. You expect the stars in the open cluster to lie in the main sequence, and then we went on to another method which was the Cepheid variables. These were stars, very bright stars, whose luminosity oscillates with time. So, there is a fixed, it exhibits a fixed periodic oscillation, and it was found that there is a period luminosity relation. So, if you could measure the period of the oscillation of the luminosity, you could predict what the luminosity should be, and from the measured flux you could determine the distance. So, the Cepheid variables could be used to determine the distances to galaxies outside our own galaxy. It was used to determine the distance to the Andromeda galaxy and to several other galaxies outside our own galaxy. Now, in addition to this, I also told you that people who are experts in spectroscopy could identify lines in the galaxy spectrum, and if the line was found to be shifted in wavelength, this shift in the wavelength could be attributed to a motion of the galaxy from which the radiation was coming. So, Hubble used independent measurements of the distances to galaxies and the velocity of the galaxies, and he found a remarkable fact. The remarkable fact was that galaxies on the average are moving away from us. Not only that, they are moving away from us with a speed proportional to the distance. This observational finding goes by the name of Hubble's law, and the constant of proportionality that relates the speed with which a galaxy is moving away from us to its distance is called the Hubble parameter. And it is believed that at present the value of the Hubble parameter, currently it is believed to be 70 kilometers per second per megaparsec, somewhere around 70 kilometers per second per megaparsec. So, if we see a galaxy at a distance of 10 megaparsec, a galaxy at a distance of 10 megaparsec, we expect it to be moving away from us with a speed that is v is equal to h naught, which is 70 kilometers per second per MPC into 10 MPC. So, that gives us 70 kilometers per second. So, a galaxy at a distance of 10 megaparsec is, we expect it to be moving away from us radially outwards with a speed 70 into 10, the distance of 700 kilometers per second. Okay. At a galaxy at a distance of 20 MPC, 20 megaparsec, we expect to be moving away from us at 140 kilometers per second, and so forth. So, this is an observational fact discovered by Hubble, and the observational fact goes by the name of Hubble's law, and the fact is that the galaxies are on the average moving away from us with a speed proportional to the distance. This was Hubble's finding. It is on the average. If you may find that there are certain deviations from this prediction, but on the average the galaxies are moving away from us with a speed proportional to the distance, and they are moving away radially outwards. So, this was an observational fact, the Hubble's law. I also told you about the cosmological principle. The cosmological principle was a kind of assumption invoked by theoreticians in the early 20th century, 1920s roughly. Theoreticians, Einstein had proposed his general theory of relativity, and theoreticians were trying to build a model for our universe based on the general theory of relativity, and to make such a model certain assumptions were required. So, these assumptions go by the name of the cosmological principle, and the cosmological principle is the assumption that the universe is homogeneous and isotropic. It essentially means that wherever I am in the universe, if I go and sit on a different galaxy, I expect to see the same thing that I see from my own galaxy, that I see in my own neighborhood. And the second thing is isotropy, whichever direction I look at, I expect to see the same thing on the average. Now, if we put together these two things, the Hubble's law of expansion, the galaxies are all moving away from us, and the cosmological principle that the universe is homogeneous and isotropic, we are led to a model of the universe where the universe is expanding. This is what we refer to as the expanding universe. It is a model for the universe. It is a way we think about the universe. So, let me explain this to you. I had started explaining this to you in the last lecture. Let me go over it again. So, the first thing that you have to realize is that the universe has no boundaries. So, this picture over here, you should realize, shows you only a part of the universe. The universe can have no boundaries. If it is homogeneous, a homogeneous universe cannot have boundaries. Why? An observer over here, if there was a boundary, an observer over here would be different from an observer sitting at the boundary. They would be different. That would break homogeneity. So, you have two possibilities. You have the possibility that the universe is infinite. It extends till infinity in all three directions, spatial directions. You also have the possibility that the universe is finite, it is compact, but it has no boundaries. And I had given you the analogy in 2 dimensions of a sphere. The surface of a sphere is compact, it has no boundaries, but it is compact. You can move in one direction and you can keep on going there, never encounter a boundary. You will come back to the same point where you started. So, a 3-dimensional analog of that is a 3-dimensional sphere. You go in one direction, you can keep on going, never hit a boundary, but you will come back to the same position after sufficient distance has been covered. For the time being, we will restrict our discussion to an infinite universe, which is conceptually much easier to visualize. So, let us just imagine an infinite universe that has no boundaries. Now, this universe, this infinite space has to be filled with galaxies, because we see galaxies in our neighborhood. Galaxies have a density roughly 0.1 per megaparsec cube. So, we expect the whole universe to be filled with galaxies like this, with a density roughly of the order of 0.1 per megaparsec cube. So, just visualize an infinite universe that extends to infinity in all directions, and the whole thing is filled with galaxies. It is filled with galaxies. Okay, there is no region which is empty. The whole thing is filled with galaxies, roughly with a density 0.1 per megaparsec cube, 0.1 galaxy per megaparsec cube, or a galaxy at roughly 2 megaparsec spacing, roughly 2 megaparsec spacing. Now, it is observed, sitting here we observe that all the galaxies are moving away from us. Now, you should not visualize that the galaxies are moving away from us into some region outside, because there is no region outside. The whole universe is filled with galaxies. the only way you can visualize this is that the whole universe is filled with galaxies and the galaxies are moving away from one another. It is not that the galaxies now are restricted in a certain region of space, outside there is vacuum and they are expanding to fill it up. No, that would break homogeneity. So, the way to visualize this fact that the galaxies are all moving away from us, since it is homogeneous, if I go and sit somewhere else in the universe, I expect to see exactly the same thing. I expect to see galaxies moving away from me. If I go and sit in the neighboring galaxy, I expect to see the same thing. So, the only way we can visualize this is that the whole universe is filled with galaxies and they are moving away from one another. Okay. So, this is what we mean by saying that the universe is expanding. The whole universe is filled with galaxies and if they move away from one another, the whole of space has to expand. The whole of space is filled with galaxies, and if the galaxies move away from one another, it means that the whole of space is actually expanding, the amount of space is increasing. So, the universe is expanding, the galaxies are moving away from one another and these galaxies fill the whole of space. So, this is what we mean by the expanding universe. I shall dwell upon this point a little bit more to make sure it is really clear, but please try to get this picture where the whole universe is filled with galaxies and they are moving away from one another. Now, if I extrapolate this expansion, this moving away from one another backward in time, so in the past the galaxies were closer, they are moving away, so in the future they will be further away from each other. So, in the past they were closer, and if I extrapolate this back in time, they will move closer and closer, and finally two galaxies will just come to the same point. Now, if two galaxies come to the same point, all the galaxies essentially come to the same point. It is a singularity that occurs, the whole space collapses to a point, and this point, so the separation between all the galaxies, which is increasing now, if I go backward in time, they will come closer and closer, and at a certain time the separation between all the galaxies becomes 0, the whole space collapses to a point, and this is what we refer to as, this is a singularity and we refer to this singularity as the Big Bang. We shall come back to this point, but what I have tried to do here is to right away mention some of the salient features of this expanding universe model. This picture illustrates some of the points that I was trying to make. So, let us visualize a part of the universe. This is a part of the universe. So, visualize this to be a part of the universe, and the whole universe is filled with galaxies. So, let us make a very simple kind of mental picture. The whole universe is filled with galaxies and it is uniform, the density has to be uniform on certain sufficiently large length scale, because the universe is homogeneous. Homogeneous means wherever I go I expect to see the same thing. So, the density of galaxies should be roughly the same everywhere. So, let us make a simple mental visualization of this. Imagine this part of the universe and we have put a grid like a graph paper in this part of the universe. So, this is a 3-dimensional grid, I have just drawn it in 2 dimensions, but just visualize a 3-dimensional grid filling this part of space. Now, like a graph paper filling this part of space, and every grid point contains a galaxy. So, there is a galaxy sitting at every grid point. Just visualize a galaxy sitting at every grid point. So, we have a galaxy sitting here, a galaxy sitting here, a galaxy sitting here, one sitting here, one sitting here, etc. So, this is a part of the universe and the galaxies are all moving away from one another. So, sometime in the future the separation between these galaxies has increased and the same part of the universe now looks like this. So, all that has happened is that the grid spacing of the graph paper has increased. So, this, just imagine that the spacing between these grid points is 1 centimeter here, and sometime in the future it becomes 2 centimeters, or 1 megaparsec, now it becomes 2 megaparsecs. Okay, so, the separation between the galaxies has increased. So, if I am sitting over here, I will see the galaxy over here moving away, because the separation is actually going up with time. So, I will see this, the distance to this galaxy, the distance to this galaxy increasing. Okay. So, this is what we mean by the expanding universe, and this is the only way we can reconcile this fact that the galaxies are all moving away from us with the fact that, with the assumption that the universe is homogeneous and isotropic. So, the whole universe is filled with galaxies like this. Extend this all the way to infinity, and in time the separation between these galaxies. So, the galaxies in this simple mental picture sit at the grid points, and the separation between these galaxies is increasing. So, in time this grid has become this, and at a later time the grid spacing is going to become even larger, and if I extrapolate it backwards, this separation becomes 0. Once the separation becomes 0, this whole thing collapses to a point. Not only this whole thing, but the infinite universe collapses to a point. Okay. So, this is the picture of the expanding universe. We shall make this more quantitative as we go along, but the correct mental picture is very important. Now, let us ask the question, is the Hubble's law? So, I have told you that we are trying to put together two things. We are trying to put together the Hubble's law of expansion along with the assumption that the universe is homogeneous and isotropic. Now, let us ask the question, very elementary question, is the Hubble's law, does the Hubble's law satisfy these conditions? Is the Hubble's law itself isotropic? Right. Now, this picture should convince you very clearly that the Hubble's law is indeed isotropic, because imagine an observer sitting here and imagine galaxies on a sphere like this at a fixed distance r. Now, Hubble's law predicts that a galaxy over here should be moving away from this observer with a speed proportional to the distance, and at every point on the sphere this is going to be exactly the same. It is going to be moving radially outwards. So, Hubble's law is isotropic. It is same irrespective of the direction. Whichever direction the observer sitting over here sees, he will see the same law of expansion. The galaxy will be moving radially outwards. So, the Hubble's law is isotropic. Now, let me convince you that the Hubble's law of expansion is homogeneous. Let me do it in one dimension. The 3-dimensional derivation is there in the slide over here, but let me first do it for you in one dimension. So, just imagine the universe is one dimensional for simplicity. It is a number line like this, and there is an observer sitting over here, O, that is the origin. Now, there is a galaxy a unit distance away, and consider another galaxy 2 unit distances away, and another one 3 unit distances away. We will not bother about what these units are. Now, consider another galaxy at -1, another one at -2, and so forth. Now, Hubble's law tells us that for an observer sitting here, this galaxy will have some velocity, and the galaxy over here will have twice the velocity, the galaxy over here will have 3 times the velocity. Similarly, the galaxy over here will have a velocity in the opposite direction, and so forth. Now, we want to verify that this is actually homogeneous. To verify that this is homogeneous, what do we mean by this being homogeneous? What we mean is, if I go and sit on some other part of the universe, at some other part of the universe, I expect to see the same thing. That is what we mean by homogeneity. So, let us consider the situation where I have an observer sitting not at this point, but at this point. So, an observer sitting at 1, my observer is now sitting here, and let us ask the question, what does this observer expect to see? This observer let us call O prime. So, this is the observer O and this is the observer O prime. So, my origin has also shifted to O prime. Now, the observer sitting at this point will be moving with the speed of this galaxy. So, the observer here has speed 1. So, the observer sitting here has speed 1. So, when I sit here, I have to transform to this frame of reference. Let us just apply the Galilean law of transformation, addition of velocities. So, an observer sitting here will see this galaxy. I have to subtract the velocity of this galaxy from this galaxy. So, this galaxy will be moving with 1. When I subtract this from this, I get 1, and then this galaxy will be moving away with speed twice this speed, and similarly the earlier observer will now be moving away from this observer with speed minus v, and this will be moving away with speed twice this speed, etc. So, what we see is that the observer sitting on this galaxy will see exactly the same Hubble's law as seen by the observer sitting on this galaxy, provided you take into account the fact that the observer sitting here is also moving with the speed of this galaxy. The same derivation can be extended to 3 dimensions. I have done it over here. I will not go into the details of this, I leave it for you to work out. It is quite simple. You have to just use, here we have done the law of addition of velocities in 1 dimension, here the law of addition of velocities has to be done vectorially. Now, I have done this derivation using the Galilean law of transformation of velocities. Now, we know that the Galilean law of transformation of velocities really is not correct. It only holds if you are going from one frame to another where the difference in the speed is quite small. If the difference in speed becomes large, then one has to use the Lorentz transformation, right. But I leave it as an exercise for you to show that the same thing also holds true if we use the Lorentz transformation. The same thing also holds true if we use the Lorentz transformation instead of the Galilean transformation. If we use the Lorentz transformation to go from one inertial frame to another, to go from one galaxy, one observer sitting on one galaxy to another observer sitting on another galaxy, if you use the Lorentz transformation, still the same analysis goes through. The Hubble's law will be exactly the same as seen by an observer sitting on a different galaxy, even if you apply the Lorentz. I leave this as an exercise for you to work out yourself. So, what have I shown you, what have I told you till now? Let me just summarize this before I go ahead. So, we have a picture for our universe, where the universe is filled with galaxies moving away from one another, and the whole universe is filled with galaxies. So, the whole of space is increasing, and this picture is essentially based on 2 things. One is Hubble's law of expansion, the other is the cosmological principle that the universe is homogeneous and isotropic. We put these 2 together, we have a picture, the expanding universe. Now, Hubble's law of expansion is an observational fact. Now, what about homogeneity and isotropy? Is the universe really homogeneous and isotropic? After all, it was just an assumption when it was introduced. Now, one has to go and verify that is the universe actually homogeneous and isotropic. Let me show you. So, one could one could address this question in a variety of ways. One approach which I shall discuss now could be to just go and map out the distribution of the galaxies. If the universe is homogeneous, we expect the galaxy distribution to be homogeneous, right. So, on certain sufficiently large length scales, we expect the galaxy distribution to be homogeneous. So, the density of galaxy should be same everywhere on a sufficiently large length scale. So, people have actually made maps of the galaxy distribution. These maps, three-dimensional galaxy distribution, these maps are what are called, based on what are called galaxy redshift surveys. So, let me explain what this is about, all about first, and then show you a few pictures. Now, measuring, okay. So, what you do is you first choose a part of the sky that you are going to survey. So, you have a part of the sky that you are going to survey, and in this part of the sky you take pictures and identify the galaxies. So, you will get certain galaxies. Now, you know the angular position of the galaxy from this. The difficult job is to determine the distances to these galaxies. It is possible to determine distances. We have discussed some of them. You could, if you can find Cepheid variables in these galaxies, you can determine the distance, but that is a very painstaking process. You have to get the period luminosity, and you can do it only for nearby galaxies. Distant galaxies, you cannot even make out the individual stars. So, there are techniques to determine distances to distant galaxies where you cannot make out the individual stars. We shall discuss those later, but what is done, it is very difficult to apply these methods to determine the distances to large numbers of galaxies. So, what is done is that you use the Hubble law of expansion to determine the distance. So, if you can measure the spectrum from the galaxy, and in this spectrum if you can identify certain spectral lines, then you can get the speed. Once you know the speed, you know Hubble's law, so you can determine the distance. Okay. So, if you can get the redshift of the galaxy, you can determine the distance. So, this is what is a galaxy redshift survey. So, one of the first redshift surveys done in the 80s, early redshift, not first, one of the early redshift surveys done in the 80s covered a strip like this on the sky, a narrow strip like this on the sky. What you do is you take a telescope and point it in a certain direction, and then as the earth rotates it will scan a certain part of the sky. So, this was done, this kind of a survey was done. So, this thickness is quite small, the extent in this direction, it is called the right ascension, is quite large, and the observer is sitting over here at the center, and these distances, the distance, this angular position is directly measured. The distance is determined from the redshift. So, that is why the distance is in units of kilometers per second. It is c into the redshift, Cz. The redshift can be directly measured, and the distance is in units of kilometers per second. So, you can directly measure the redshift from the shift in the wavelength. C into Z gives you the speed, and this from Hubble's law is h naught r. So, if you divide this by h naught, or you get the distance. So, this was one of the first redshift survey. It is called the CFA, Harvard Smith, carried out by the Harvard Smithsonian Center for Astrophysics, CFA. So, it is the CFA redshift survey. Each point over here is a galaxy now. Each point in this diagram is a galaxy. So, the distance, this picture shows you the three-dimensional distribution of galaxies in a thin region of space. The thickness has been suppressed because the region that has been surveyed is quite thin, and this, the distances, the speed, the CZ value or the speed v of the galaxies is of the order of tens of thousands of kilometers. So, if I have, let us say, 10,000 kilometers per second, so if I convert this to distance divided by 100 kilometers per second per MPC, this extends to of the order of something like 100 MPC. So, the extent of these redshift surveys is of the order of 100 MPC, not more than that, and it has mapped out a nearby, it is actually less than that, and it has mapped out the distribution of galaxies in a nearby part of the universe only. There are of the order of 1000 galaxies, not more than that, and what we see is that the galaxies show this kind of a very strange pattern. It is definitely not homogeneous, you would not call this homogeneous. This very weird looking structure that you see over here has been, looks like a man in the sky, and this has been given the name the man in the sky. It is actually, what you see over here is actually a cluster of galaxies called the Coma cluster, and this pattern, this very strange pattern that you see, is a consequence of the fact that this cluster of galaxies is a gravitationally bound object. The galaxies inside this cluster, so we have a region like this and there are galaxies which are gravitationally bound inside this. If the galaxies are gravitationally bound, they are really not moving away from one another according to Hubble's law of expansion. They have deviations. So, there is some kind of large deviations from Hubble law of expansion in this region. So, we are an observer sitting over here. This whole region is approximately moving away from us according to Hubble's law of expansion, but the individual galaxies have their own motion due to the presence of this cluster of galaxies. This is a point that we shall come back to, and it is this deviations from the Hubble's law which appears as this very strange looking structure over here. Now, this is what was available in the 80s and in the 70s actually, not in the 80s, late 70s, early 80s. Now, in the 80s, people did much larger redshift surveys. So, here you have the Las Campanas redshift survey, which has tens of thousands of galaxies, and it extends much further. There are 3 thin strips in the northern galactic pole region and 3 thin strips in the southern galactic pole region, and together they have around tens of thousands of galaxies. Now, you see that this has mapped out a reasonably significant part of the universe, and what you see is that the galaxies exhibit structure. The galaxies seem to be distributed in some kind of a interconnected network of filaments encircling voids. There are large voids over here, if you can make out in this picture. There are regions here with very little galaxies, here with very little galaxies, and the galaxies are distributed in the boundaries of these regions. They have some kind of a filamentary pattern. These filaments are interconnected into what is called the cosmic web, as you go further and further away, the number of galaxies keeps on reducing, but this is just an observational effect, because the galaxies as you go further away gets fainter and get fainter and fainter, you do not see them, that is all, they are there. This is something you can correct for. Now, this distribution of galaxies exhibits structures, but if you, so the question arises, does this distribution of galaxies ever become homogeneous? Right, like let us take a solid, let us just discuss it in terms of a solid. In a solid, this, let us take this wood, the table or the wall or any such material, solid material. Now, for certain purposes we can think of the solid as being homogeneous. If you are dealing with elastic properties of the solid, you can think of it as being homogeneous. But if you ask, is the solid really homogeneous? At a microscopic level, there are atoms. In certain places you will find the atoms, in certain places you will not find atoms. So, at a microscopic scale, the solid is not homogeneous. There are atoms and then there are regions with no atoms. So, it is not homogeneous, but if you average it, so there are these, in a solid there are these particles, but if I average it, if I look at the average properties over a sufficiently large region, then I can think of, if I average over a sufficiently large region, I can think of as the solid as being homogeneous, the properties being the same everywhere. Similarly, with the galaxy distribution, so if I look at it closely, if I look at it at a small length scale, at a close length scale, small length scale, if I look at the picture from very close, I will see all kinds of patterns and structures in the galaxy distribution. But the question arises, is there a length scale sufficiently large, if I smooth over it, that the galaxy distribution becomes homogeneous? And such an analysis can be done, it has been done, and it turns out that the distribution of galaxies becomes homogeneous at length scales of around 80 to 100 megaparsec. So, if I put circles of radius of the order of 80 to 100 MPC in this picture, then the galaxy distribution becomes homogeneous. So, the galaxy distribution does indicate homogeneity, the galaxy distribution does indicate homogeneity, provided we are on we average the galaxy distribution of over length scales of the order of 80 to 100 megaparsecs. On smaller scales, we have structures in the galaxy distribution. This shows you a even later survey, the 2-degree field galaxy redshift survey. This was done in the 90s, completed in the 90s. It has 100,000 of the order of hundreds of thousands of galaxies, and here again you can see the structures much more prominent. You see this pattern, there are these voids, and these voids are surrounded by regions which have galaxies, they look like filaments, and these filaments are interconnected into what is called the cosmic web. So, understanding this structure is very important, but that is not of our interest now. The question that we are interested in is this homogeneous on certain sufficiently large scales? This shows you another redshift survey which is called the Sloan Digital Sky Survey. This sky survey is currently still operational. It will measure the redshift, it has already measured, I think it is over now, it has measured the redshift of millions, of a million galaxies, and it is truly 3-dimensional in nature. The earlier ones, this and this, were 2-dimensional in the sense that they went out in depth and in one angular direction, not in two angular directions. The Sloan Digital Sky Survey is really 3-dimensional. It has mapped out the distribution of galaxies in 3 dimensions, and millions of the order of 1 million galaxy, the positions have been mapped out, and there is evidence that the galaxy distribution becomes homogeneous on length scales of the order of 80 to 100 megaparsec. Now, let me very quickly tell you about another indication that the universe is isotropic. This is the cosmic microwave background radiation. This picture shows you the people who discovered this, Penzias and Wilson, and this is a topic that I shall come back to in detail, much more detail later. But the fact is that there is a radiation which coming to us from all directions. This radiation has been found to have a black body spectrum. So, if you look at the spectrum of this radiation, it has a black body spectrum, the Planckian black body spectrum, with a temperature corresponding to a temperature of 2.73 Kelvin. So, this radiation is coming to us from all directions. This radiation is believed to be cosmological in origin, that is, it is a radiation which fills the whole universe, just like the galaxies we believe fills the whole universe. This is a radiation that fills the whole universe, and this radiation is observed to have a temperature of 2.73 Kelvin. Now, you can take a radio receiver, radio antenna, and point it in different direction and ask the question, is this radiation isotropic? It has been found that the radiation is isotropic to a high degree of accuracy. So, there are angular fluctuations in the temperature delta T, such that delta T by T, that is the mean temperature, is of the order of 10 to the power minus 5 tens of microkelvin, of the order of tens of microkelvin. So, to an order, it is isotropic to an accuracy of 1 in 10 to the power 5. So, this is a very high order of isotropy, and this is one of the most important evidences that the universe is isotropic and homogeneous also, because unless, well, there is a possibility from this that the CMBR may be, that it may be isotropic just around us, but there are several evidences which indicate that the universe is homogeneous and isotropic. I have discussed 2 of them over here. Now, we would like to make a model, try to understand the expansion of the universe. To understand the expansion, to get a good understanding of the expansion of the universe, and to work out its mathematics, to work out the to quantify this, it is useful to consider what is called a Comoving coordinate system. What is a Comoving coordinate system? This picture over here illustrates what I mean by a Comoving coordinate system. The galaxies, I have told you, the way we infer the Hubble's law and the cosmological principle is in terms of the galaxies moving away from one another. Let us consider a coordinate system x that remains fixed to these galaxies, and this coordinate system is called the Comoving coordinate system. So, let us consider a coordinate system that remains fixed to these galaxies. So, here we have I have told you that we will visualize the galaxies, a galaxy sitting at every grid point, and the galaxies are all moving away from one another. So, if we have a coordinate system which is fixed to these galaxies, at a later time the coordinate system looks like this. It is fixed to the galaxies. Let us say that the origin is at this point over here. The origin is at this point over here. Sorry, not this point, is at this point over here. This is the origin. So, the origin is this point over here, this point over here, the one over here. Now, this point has coordinate 0 1, 1 0, x axis is 1, y axis is 0. Same, the coordinate of this point remains fixed. The coordinate of this galaxy in this coordinate system, the coordinate of this particular galaxy and this galaxy over here, it remains fixed. The galaxy continues to have coordinate 1 0 0 with respect to the origin. Now, if I ask you what is the position of this galaxy, this particular galaxy whose coordinate in this comoving coordinate system is 1 0 0, its position has actually changed because the galaxies are moving away from one another. Now, this change in this position of the galaxy has been incorporated into the expansion of the coordinate system itself. Okay. So, the comoving coordinates, the galaxies are all moving away from one another, the comoving coordinates of the galaxies remain fixed, but the physical position R is related to the comoving coordinate through a factor A of t, which changes with time. So, this is called the proper coordinate. X is the comoving coordinate, R is the proper distance or the proper position, proper coordinate of the galaxy. So, we have introduced a coordinate system which is expanding with the galaxies. So, the position of the galaxies remains fixed. The spacing between these grid points increases, is given, is changes according to this function A of t called the scale factor. It is a function of time. So, the position of the galaxy R is also a function of time, A is a function of time, but its comoving coordinate remains fixed as it expands. So, we have introduced a coordinate system that expands with the universe. In this coordinate system, the galaxy positions as they move away from one another remain fixed. So, this is the comoving coordinate, and in this coordinate, so you can see in this coordinate the galaxy positions remain fixed, but the galaxies are actually moving away from one another because the spacing between these coordinates have changed. Okay. Now, let us ask the question, an observer is sitting at the origin over here, what is the speed with which a galaxy at a fixed comoving coordinate moves away? So, this can be calculated by just calculating the time derivative of A. So, the position of the galaxy is given by R as a function of time, and that is the scale factor into x, and its speed v can be calculated by just differentiating R with respect to time. Now, as the universe expands, the comoving coordinate of the galaxy does not change, but its scale factor changes. So, we have A dot, where A dot is the time derivative of A into x, and this can be written as A dot by A t into A into x, and A into x is R. So, at any instant of time, the speed with which a galaxy is moving away from an observer sitting at the origin is proportional to the distance of the galaxy. And at present, if I do this, if I take this and apply it at present, then the speed is h, okay, at any given time h naught r. So, at present, or at any time for that matter, we know that at any time instant t, so the Hubble parameter h of t is A dot by A, and it could be a function of time, and at present we know that the Hubble parameter has a value h naught, So, this is A dot by A at the time t equal to t naught, the present time. So, we have seen, we have learned quite a few things here. First thing was that we introduced a comoving coordinate system. So, this is a coordinate system which is expanding with the galaxies. So, we have a picture where the galaxies are moving away from one another, and we have a coordinate system which is expanding with these, moving away, which is fixed with these galaxies, called the comoving coordinate system. And the expansion, the motion of the galaxies has been put into a function called the scale factor A of t. Now, once we make this kind of an assumption, we found that what you see sitting at a fixed position is exactly Hubble's law, and the Hubble parameter h at any given time is related to the time derivative of the scale factor divided by the value of the scale factor. And at present h naught is A dot by A at t equal to the present value. Now, suppose we ignore the effect of gravity. Let us just take up a simple situation where I ignore the effect of gravity. So, if I ignore the effect of gravity, a galaxy, the speed at which a galaxy is moving, which is A dot into x, A dot t into x, let me write this again. So, if I calculate the speed every galaxy is moving is at a fixed x. So, it is its motion r of t, its proper position is related to its comoving coordinate through this scale factor t. Now, the speed with which it is moving is A dot x, and its acceleration at any instant of time, A is its, let me just write it as v dot t is A double dot t into x, and if there is no gravity, there is no force acting on the galaxy. So, this should be 0. So, if it is free expansion, the second derivative of the scale factor should be 0, or we know the solution to this equation A of t, the scale factor, will be some constant b into time plus another constant k. This is the most general solution. Now, if I plot this, it will be a straight line. Now, the value of k will decide where the scale factor becomes 0. It is most convenient to choose this value of k so that the scale factor is 0 at t equal to 0. Scale factor, so that is A of t is equal to b t. This is the law of expansion in the absence of gravity, free expansion. Now, just see what happens at t equal to 0, the scale factor is 0. Once the scale factor becomes 0, all the galaxies, irrespective of what their comoving coordinate is, all galaxies are at the same point 0. Once the scale factor is 0, all the galaxies over here, all these galaxies have collapsed to the origin. Not only this, but the infinite universe has collapsed to the origin. Okay, so this is the singularity which we call the Big Bang. So, t equal to 0, A is equal to 0, and this is what we call the Big Bang. Now, in this model, let me also calculate the Hubble parameter. The Hubble parameter h as a function of time is A dot by A, and A dot by A, so I have to differentiate this. A dot is equal to B. So, A dot by A is B by BT, which gives me 1 by time. So, if I think of the universe originating the starting at t equal to 0, the Big Bang, because we cannot conceive of the universe beyond the singularity. If I extrapolate backwards, I cannot conceive of the universe after it collapses, before what happened before it collapses. The whole physics breaks down, the whole universe collapses to a point. So, we talk about the Big Bang as the origin of the universe as far as we understand originated at this point t equal to 0. So, this t over here is the time that elapsed since that instant. So, we can talk about this t as the age of the universe. So, in this model at any given instant of time, the Hubble parameter is the inverse of the age of the universe. Okay. So, in this model the expansion law is very simple. A as a function of time is a straight line and the Hubble parameter is the inverse of the age of the universe. So, I leave it to you to work out I leave it to you to work out the age of the universe in this model, assuming that the Hubble parameter is 100 h kilometer per second per MPC. You can straight away determine the age of the universe according to this model of free expansion. Okay, so, please do this exercise and we shall resume our discussion from here in the next lecture.